In Solutions 9, we're going to continue our discussion of acid-base dissociation and specifically define strong acids and strong bases and compare those to weak acids and weak bases. Here I have a solution of water. I want you to look at the bottom beneath the beaker and look at the equation represented here. We have water molecules dissociating into hydronium and hydroxide molecules. This phenomena is known as the autoionization of water, and it is something we will discuss in AP chemistry. For now, I want you to simply look at this and look at the pH paper and the pH scale. Now, as you know, water is neutral. Water has a pH of 7. If we go and now look at a strong acid, I want you to again start by looking down at the equation. This is the same dissociation as we saw in the previous podcast, where we have a strong acid in an aqueous environment and it completely dissociates. The arrow is one way to the right into an anion along with a hydronium cation. In the schematic, look at the red molecules which represent hydronium. Hydronium is what makes an acid strong. The more concentrated the hydronium ions are, the stronger the acid. Let me take my pH paper here and dip it in, and we can see that we are over here on this end where a pH between, say, 1 and 2 would indicate that this is an acid. So to define this, any acid or base that dissociates 100% into its ions. Again, that's what this yield one direction arrow means. Everything will push to the right and form hydronium ions and the anion of the acid in this case. And these are defined as either strong bases or strong acids. Let's look at our dissociation of a strong acid. Hydrochloric is going to push 100% to the right and dissociate into hydronium, which means if we were to find the pH of hydrochloric acid, it would be very low, which is indicative of a strong acid. Now I'm going to look at a weak acid here on the simulation. Start with the equation on the bottom. And first and foremost, note that we have an equilibrium. It points both directions, showing these species are all present in varying concentrations. And if you look at the beaker, you can see most of the chemical species are the weak acid. In other words, we don't see as many of the hydronium cations. So if I take my pH paper and dip it in, okay, we can see that we still have an acid. We have a pH less than 7, but this is a relatively weak acid. Let's move on and look at a strong base. Start with the equation, complete dissociation. Now go to the beaker, and you'll see most species that are present are the hydroxide anions along with the cation from the chemical species here. Say sodium cation, or potassium cations. The point being is that they have almost completely dissociated. Now, the more hydroxides there are in solution, the more basic. In other words, the higher the pH. So let's go ahead and dip it in, and we see we have maybe 13 or so for the pH, which means that we have a strong base. Lastly, we can look at a weak base, look at the dissociation equation, note the equilibrium arrows pointing both directions. Note the abundance of the weak base. Most of the solution is comprised of the weak base. There are relatively few hydroxide anions, therefore we would predict that this would be a weak base. due to the fact there are not many hydroxides in solution, and indeed it is a weak base, perhaps around 10 or so on the pH scale. So let's define the 6 strong acids. These 6 acids you will need to commit to memory. What's nice about this is if you know the 6, perchloric, sulfuric, hydroiodic, hydrobromic, hydrochloric, and nitric, you know the 6, then what that means is that the remaining acids are weak. So this is nice. If you can memorize these 6, then all others are considered weak acids. And weak acids only partially dissociate into their hydronium and the anion. Likewise, a weak base would be the same, and we're going to get to those in a minute. On the right here, you can see our schematic. We have a pH of 2. We have an abundance of hydronium ions, as I showed in the simulation at the beginning of this video. These 6 here, several of them you can memorize because we've used them. We've used nitric acid, we've used hydrochloric acid, we've used sulfuric acid. Then you can look at hydroiodic and hydrobromic. Notice those are halogens that have accepted a proton in an aqueous environment. And then perchloric acid, number 1, very strong acid. We don't have any perchloric acid in our lab. Along with, we do not have any hydroiodic or hydrobromic acids either. So here we have a definition. Now, let us go ahead and look at the fact that when strong acids dissociate, their conjugate bases are weak. So a strong acid has a weak conjugate base. Now we can go ahead and look at our strong bases. Groups 1 and 2 are considered strong, which means that they will completely dissociate into their ions, which means they will form many hydroxides. And remember, that's what makes the solution basic, is the presence of the hydroxide ions. So we have all groups 1 and 2. So you can consider, say, lithium hydroxide. That's a strong base because it will completely dissociate into a lithium cation and hydroxide anions in an aqueous environment. All right. I also want you to then look at your group 2. So I have an example here of magnesium, and you can look at the magnesium dissociation here, and you can note for every mole of magnesium hydroxide, it will dissociate into 1 mole of the cation and 2 moles of the hydroxide anion. So we're looking at our ratios there as well. We can look at our schematic. We have a high pH of 12. That is due to the presence of all the hydroxide anions in the solution. Weak acids will only partially dissociate into ions. So here in the schematic, you can see there are relatively few hydronium cations because the acid has mostly stayed intact. And you can see that in the schematic here, that the majority of the molecules present here are the acid, and the weak acid has only partially dissociated. Let's look at examples. Now recall, if you memorize the 6 strongs, which you should have written down, all the others are weak, which means all the others partially dissociate into ions. So it's quite simple to be able to identify a strong acid, a weak acid, and likewise a strong base and a weak base. And that's something you are expected to know how to do in this course. So we have hydrofluoric, water, nitrous, carbonic, acetic. These are all examples of weak acids. Okay, so if we look at the dissociation here of nitrous acid, we're showing it here with water. Note the two-way equilibrium arrow. It will dissociate only partially into the nitrite anion and the hydronium ion. If we were to put a percent dissociation to this, we could say maybe only 5% dissociate into hydronium, whereas in our strong acids, 100% dissociation occurs. These percentages are just estimates. It could be 98% of the weak acid remains intact as the weak acid, while only 2% would dissociate into hydronium. All right, so now we can look at our weak base. Let's continue to look at ammonium, which is a weak base. And ammonium in water will partially dissociate into ammonium and hydroxide. Again, the hydroxides are what make the solution basic. In this case here, we have a pH of 9.5, which is greater than 7, which means overall the solution is basic. However, you can see in the majority of these solutes and ions here in this are simply the intact ammonium, whereas relatively few of them are the hydroxide ion. So if we put percentages here, we would show that a very small percentage will dissociate into hydroxide ions, which results in a weak basic solution. In our Georgia Standards of Excellence, we're continuing to look at the nature of acids and bases. We're looking at percent dissociation. We're looking at pH, and very soon we will start to perform some titrations in class to help us explore acid-base neutralization. I will see you guys in class.